Yeah, today we're very, very happy to have a frontier condensed matter physics seminar series. We invited Rob McQueeney, who's a chair professor at the Ames laboratory in Iowa State University. He's sort of a fellow neutron scattering person who understand dynamics and in the 166 materials. He's done some wonderful work recently. So I wanted to hear a lot of his talk on this class of materials. Yeah, so that's why I invited him. So Rob, you agree that your talk will be recorded and posted, right?
Yeah, that's fine.
Okay. Yeah. Thank you very much. Yeah, Rob, it's all yours.
Okay. So first, I want to thank you guys for asking me to give this talk. I went through sort of the archive of the talks that you had. You guys have this nice site where you can look at all the old talks. So I learned quite a bit already without even coming here to get my questions asked. But so today I'm going to talk a little bit about the magnetism in these Kagome metals, which have a chemical formula 166. So, the first thing I'll do is describe, how you have these novel electronic bands in Kagome metals, which arise due to the geometrically frustrated lattice, and bringing things like Dirac cones, Van Hove singularities, or flat bands close to EF can give rise to lots of novel properties. So in this talk, I'm going to focus a little bit more on the magnetism of these materials. So certainly the magnetism can interact with the Kagome layers. There's a lot of functionality there. But my main objectives here is to understand how magnetic interactions can lead to a variety of these observed phases and how the spin dynamics can control magnetic phase transitions similar to this phase diagram I showed here. Also, in the context of just looking at these materials with inelastic neutron scattering, we find unusual excitations, magnetic excitations, which I call emergent magnetic excitations, which may provide a window into sort of hybridized magnetic and electronic states that exist within the Kagome layer. And also, these materials are interesting because they're chiral materials. You can have helical order. You can have magnetically field-driven phases that have topological Hall, which indicates maybe some scalar spin chirality. So I'll spend a little bit of time talking about the origins of this spin chirality from the viewpoint of neutrons. So my outline here is then to briefly introduce these Kagome metals, talk a little bit about how rare earth magnetism plays a crucial role in the development of the properties of these materials. We did a lot of work developing a magnetic model for these R166 compounds, which we can apply to inelastic neutron scattering. We can predict magnetic phases and so forth. And then I'll talk a little bit more about the aspects of spin chirality in these materials. And if time allows, maybe even talk a little bit about magnonics and chiral magnonics in these materials. So before I get started, I just want to introduce my collaborators. So we have a large scattering group at the Ames laboratory. I have here underlined students and postdocs who are doing their PhD work or other work on these compounds. We also have strong support from a density functional theory at Ames. For those of you who might know, I also lucky to direct an energy frontier research center called CATS. Part of the CATS focuses on Kagome materials and flat band materials. So we do get support for things like crystal growth and characterization, theory, high field measurements, and so forth from the CATS Center. Of course, we do most of our, if not all of our, neutron scattering at Oak Ridge National Laboratory. So we use a variety of instruments there. And we also have external collaborators here. I noticed Jeff's in the audience. So Jeff and I have done some stuff on the terbium and the yttrium 166 compounds, and that collaboration is continuing. So I'm just now going to give a brief introduction on the Kagome metals. Oh, by the way, I know that the format of this is kind of loose, so please feel free to interrupt me if you have any questions. I'm just going to try to play it a little bit loose and easy in this talk. So, the big story about Kagome metals, and I don't know how much I have to talk about this group, is that you have these this motif of corner shared triangles, which leads to geometric frustration. Now, if we have local moment insulator, that can lead to unique magnetic states like spin liquids. But in a metal, this geometric frustration can lead to the localization of electronic states. So here, for example, I show what's called a compact localized state, which consists of an electronic state which is localized due to destructive interference of the hopping on this geometrically frustrated lattice. And so this compact localized state in reciprocal space leads to a flat electronic band. That flat band can have a high electronic density of states. So Kagome metals are susceptible to a variety of correlation-driven phenomena or ground states, such as itinerant magnetism, charge density waves, superconductivity, and so on. You also have, as a consequence of this frustrated geometry, other features in the bands, such as Van Hove singularities, which can also lead to correlation-driven phenomena, especially charge density waves. And you can also have Dirac cones, which can interact with time reversal symmetry breaking or other crystallographic symmetry breaking to give you things like Weil semi-metals or Chern insulators. So there's a lot going on in these materials. There's a growing class of materials realizations of these Kagome metals. So for example, we have these transition metal stanides and transition metal germanides. You find these Kagome layers, which are separated by a variety of different non-magnetic layers or non-Kagome layers. And so within this family of materials like cobalt tin, nickel 3 indium, these are sort of correlated metals on the verge of magnetic order. You have materials like iron tin and iron 3 tin 2, which are itinerant ferromagnets, iron germanium, which a lot of people in this audience are familiar with, where you can get antiferromagnetic order in concert with charge density wave order, and materials like manganese 3X, which are Weil semi-metals. There's also this very heavily studied class of materials called 135. These are non-magnetic materials, but the Van Hove singularity can drive charge density wave order and superconductivity. Cobalt 3, tin 2, sulfur 2 is another class of materials, these shandite compounds, which are probably one of the better known examples of ferromagnetic Weil semi-metal. And here, the materials I'll talk about are these rare earth transition metal 6, X6, where X can be tin or germanium. These are known for the character of the Kagome bands in their Kagome layers, but they're more known, at least in the past, for their complex magnetism. So I'll spend a lot of time talking about that complex magnetism and how it relates to the Kagome layers. So just a little bit of history of these 166 compounds. So these 166 compounds were studied early on because they're a good example of permanent magnets, which you can get from a combination of a rare earth and a transition metal compound. So one recipe for, say, hard permanent magnets is to have a compound where Tc is very large due to strong transition metal exchange. But you can also make the materials, those compounds, very hard by introducing rare earths, which have a very strong magnetic anisotropy. And so the coupling between the rare earth and the transition metal, of course, is necessary to get these hard permanent magnets. And so there's typically this RT exchange is antiferromagnetic. So you'll get ferrimagnetic compounds. Examples are like these rare earth iron boron, rare earth cobalt 5, rare earth 2 iron 17. These are technologically important permanent magnets. So you can buy these neodymium iron boron magnets. And these materials are complex. They have multiple magnetic sublattices, spin reorientation transitions, metamagnetism, and so on. So these R166 compounds, specifically the ones where the transition metal is manganese, were studied for that purpose early in the 90s. So this is just some older data, so going back as far as 1991, where people understood these materials as sort of satisfying these criteria for permanent magnets. They're ferrimagnets. In the case of terbium, these are uniaxial ferrimagnets with a very high transition temperature above 400 Kelvin. And so a lot of these materials, different rare earths, different tin and germanium compounds were studied early on. In the later 90s, people began to grow single crystals of these materials. And so these are some of the first data showing evidence for strong metamagnetic transitions, in this case in terbium manganese 6-tin-6. And again, just this 3-site chemical structure with 2 magnetic sublattices allows for a large degree of tunability via chemical substitution, for example. The other thing of interest in this class of compounds is the electronic bands. So when you vary the transition metal, you can almost think of that like band filling. So, and that can move different topological features or different band features close to EF. So for example, the rare earth vanadium-6-tin-6 is probably the closest in this set of materials to being a Dirac semi-metal. You find a Dirac cone which is very close to EF, just above EF. This has a large Berry curvature, and so, for example, people have reported gigantic orbital magnetization in applied fields where a very small field can lead to a large splitting of this Dirac cone and a large orbital moment. The chromium compounds are probably the closest we have to these 166 compounds to being a flat band material. This shows some ARPAS data where you have a flat band very close to EF. These materials are non-magnetic, but they show sort of stoner-enhanced behavior. So it's likely that chemical substitutions or any study of these materials may reveal sort of ordered or symmetry-broken ground states that are driven by flat bands. The rare earth manganese-6-tin-6, out of these three compounds, it's the only one where the Kagome layer itself orders magnetically. And so again, you have this two sublattice magnetization. The coupling, the exchange coupling is very large. So the Dirac cones near the Fermi energy are exchange split. So you get a spin polarized Dirac cone. In the presence of large spin orbit coupling, you can split that spin polarized Dirac cone to give you a Chern insulator. This was proposed in 2020, which I think really kicked off a lot of the interest in these materials as platforms for topological states of matter. And in the subsequent years, people have looked at a variety of these rare earth manganese-6-tin-6 compounds, studying things like the behavior of Dirac cones for different rare earths. So here, studying quantum oscillations, or in the yttrium manganese-6-tin-6, looking for evidence of where the flat bands and the Dirac cones are by ARPAS. So this sets up a lot of the motivation where in the early 90s and 2000s, people were interested in the magnetic sort of subset. And then in the 2020s, people started to couple this magnetism to the topological bands. So now I'm going to spend a little bit of time introducing in more detail the magnetism of these rare earth manganese-6-tin-6 compounds. So there are three essential things, essential magnetic interactions that these compounds have. And if we can understand and parameterize these interactions, we can get a very detailed understanding of the magnetism. So the first thing is that the interactions between manganese within the layer are very strong and very ferromagnetic. So the structure here in these 166 compounds consists of a bilayer of manganese Kagome layers, which are separated by a single triangular rare earth layer. And so because of this strong ferromagnetic interaction here, we can think of all of these layers, individual layers themselves, as being ferromagnetic. And so the real richness, at least at zero field, of these magnetic structures has to do with the arrangement of these ferromagnetic layers. And so when the rare earth is magnetic, and it's sort of one of the lighter rare earths, these tend to form ferrimagnets, as I described before. So terbium is probably the one that's been the most studied. Terbium has a strong uniaxial anisotropy, so you get this picture here, which is a uniaxial ferrimagnet. However, other rare earths have different magnetic anisotropies. So for example, gadolinium and erbium have an easy plane anisotropy. So these are also collinear ferrimagnets, but the moments lie in the plane. And in dysprosium and holmium, these have a more complex magnetic anisotropy landscape, and these actually prefer to be tilted away from the C-axis by some angle, around 45 degrees, but they're also nominally ferrimagnetic. So understanding the role of, let me put on this pointer here. Understanding the role of rare earth magnetic anisotropy is essential to understand the overall magnetism. And finally, when the rare earth is not magnetic, or the coupling between the manganese and a magnetic rare earth is weak, for example, in thulium, then these materials tend to adopt a helical or a spiral order along the c-axis. So here is an example in yttrium manganese 6 tin 6. Each layer, again, which is ferromagnetic, the magnetic moment direction turns some angle layer to layer. And we understand the development of this sort of helical magnetism as arising from the competition between different interlayer interactions, either between manganese layers or between rare earth and manganese layers. So these three ingredients, strong ferromagnetism within the layers, rare earth magnetic anisotropy, which can be quite strong, and these competing interlayer actions, these are the three things that need to be sort of understood to understand how the magnetism develops. So the first thing I'll talk about is the rare earth magnetic anisotropy. So this is just a picture here of a rare earth, in this case terbium, in its local crystalline environment. Now terbium is a 4f8, so it's one electron beyond half filled, so that electron occupies a state with high orbital angular momentum. So the terbium ion itself, its orbit is kind of flat and very anisotropic, right? And so as you move through the rare earths, of course, that anisotropy changes as I start to fill different f orbits. And because of the large spin orbit coupling in rare earths, that the orbits will respond to the crystalline electric field and they will find a position which minimizes the electrostatic energy, and they will take the magnetic moment with them as they rotate. So typically people would think of the magnetocrystalline anisotropy, sort of the classical magnetocrystalline anisotropy, as having two parameters, K1 and K2, which determine the magnetic anisotropy landscape as I tip the moment away from the c-axis. And so these two K1 and K2 terms depend on these ALM coefficients. These are just the sort of spherical harmonics that describe the crystalline electric field potential, and these quantities Q2 and Q4. And these Q2 and Q4 in the classical sense are the parameters which describe the orbital shape of the rare earth. So if we look at these 166 compounds, maybe it's not so obvious here, but one of the interesting things about these 166 compounds is this Q4 term is very large. And so what that means is that depending on the sign of Q4, you'll either get a large barrier for rotation of the moments in the polar direction, or you'll get a sort of a maximum in Q4, or you'll get a minimum in Q4, which will then tip the equilibrium moment away from the c-axis. So here we have a table that shows terbium, dysprosium, holmium, and erbium, so we can understand the general features of the magnetic anisotropy by looking at the signs of Q2 and Q4. And so for terbium, right, the orbital is satisfied with the orbital angular momentum pointing up and the spin pointing up. So this gives me a strong uniaxial anisotropy. If I look at this plot here, this is the anisotropy as a function of angle calculated from DFT. And so we can see here that this Q4 term then introduces a barrier when I try to rotate the sample away from the c-axis. It's a huge energy, magnetic anisotropy energy, that favors uniaxial ferrimagnetism. For dysprosium and holmium, you see that actually this Q4 contribution is negative. So dysprosium and holmium, the minimum in the anisotropy energy is somewhere in between uniaxial and planar. It's about 45 degrees. And that has to do with this orbital shape being happy, sort of turned a little bit such that it minimizes its electrostatic energy. And finally, the erbium, you can see that it favors being in a uniaxial geometry, but just slightly. Even though there's a large barrier to rotate the angle in the plane, the minimum in the planar direction and the uniaxial direction, the difference is very small. So you would expect erbium then to be sort of on the borderline between uniaxial and easy plane magnetism. And the DFT also shows that the manganese in all cases for all rare earths is always easy plane. So when we have, say, terbium and manganese, the terbium is is uniaxial, the manganese is easy plane. So the ultimate magnetic order will depend on the balance or the competition between these two anisotropies. So another thing that comes in because of this complex magnetic anisotropy landscape is that you have tunable magnetism and metamagnetism throughout the series. So for example, on the left here, I show different rare earth 166 compounds, terbium, dysprosium, holmium, gadolinium, and erbium. So we see that, as I just described, at zero temperature, the terbium is uniaxial, holmium and dysprosium are tilted, and erbium and gadolinium are planar, but all of them evolve to a planar ferrimagnetic state at high temperatures. The reason is that thermal fluctuations of the rare earth moments will quench the anisotropy, so the manganese easy plane anisotropy will always win. And the details of these transitions, whether they're first order or second order, just depend on this landscape. So for terbium, because I have a barrier here going from the uniaxial to the planar ferrimagnet, that transition is always first order. The other thing we can have is field-driven transitions. So I had mentioned here that erbium, the difference between uniaxial and easy plane for the erbium, that's a very small energy. So I would expect, even though I'm in the planar phase, a small field along the c-axis will give me a ferrimagnetic along c. And so that's in fact the case. So here you see a metamagnetic transition where the moment rotates from planar to c-axis with a very small field, less than 1 Tesla. So other rare earth 166 compounds, they have a variety of metamagnetic transitions in very high fields. So for holmium, for example, this is a tilted ferrimagnet, but we can have metamagnetic transitions to different canted phases. And for thulium manganese 6-tin-6, which is a low temperature helix, we can have things like novel field-driven helical to collinear transitions. So there's a lot of exciting magnetism going on in these materials. And so one more bit about these interlayer competing interactions and chirality. So chirality can develop either in the ground state or it can develop spontaneously as a function of temperature in these compounds. So here, for example, I show a mean field calculation of the spiral angle as a function of the coupling between the rare earth and the manganese. So for yttrium 166, of course, yttrium is not magnetic. So this coupling is 0. And so yttrium will naturally form a spiral with an angle of about 90 degrees, a pitch angle of about 90 degrees, which is what's observed experimentally. However, when I introduce this antiferromagnetic coupling between the rare earth and the manganese, that stabilizes the ferrimagnetic phase. So it's like an effective interlayer interaction that stabilizes this phase. So for erbium 166, that native parameter puts it within the ferrimagnetic phase. But it's easy to see that it doesn't take, I don't have to lower this exchange too much to go from the ferrimagnetic to the spiral phase. And so for erbium manganese 6-tin-6, we can soften this effective interaction again through thermal fluctuations of the erbium. And so we have a temperature-driven transition in the erbium between a ferrimagnet and a spiral. So this is neutron diffraction data where you see Q equals 0, magnetic Bragg peak split into incommensurate peaks as a function of temperature.
So Rob, I mean, for this chiral phase, spiral phase, is it really chiral or is, sort of a not chiral?
Well, it has a vector chirality. I mean,
okay, so
SI cross SJ, yeah.
Okay, so it does have SI cross SJ that now equal to 0.
Right, but you have domains.
Oh, okay, so you have both left and right hand domains.
Right.
Okay,
Yeah, right.
Understood. Thank you.
So the other interesting thing is if in these materials, which also was another motivation to kind of revisit these materials, is that if you start in a spiral phase and you apply a field in the plane of the spiral, you get a variety of distorted spiral or conical phases or fan-like phases. And so one of these phases in particular, this TCS is a transverse conical spiral phase, people have observed a large topological Hall effect both in this case in the yttrium and the erbium. And so most people would associate topological Hall effect with the development of scalar spin chirality. And so this is an interesting and open question because in principle, the TCS phase does not have, it may have a non-zero scalar spin chirality per se, but it doesn't have an attendant emergent chiral field that would give you a topological Hall. So I'll talk a little bit more about that later. So taking all these kind of history of these materials into account, we can develop sort of a minimalistic magnetic model for these compounds. So we have three different contributions. The first is exchange. And so I already told you that the intralayer exchange between manganese is very strong and ferromagnetic. It's also true that the coupling between these manganese bilayers is very strong and ferromagnetic. This is called J2 here. And so on the other hand, because we have helical magnetism, we know that there must be competing interlayer interactions. And so the first two would be this J1. This is between Kagome layers with a rare earth layer in between, and J3, which is the coupling between like Kagome layers. And so in order to get a helix, one must have the product of these two interactions be less than 0. So one must be ferro, one must be antiferro, and their ratio must be close to 2. Or J1 over J3 must be close to 2. And finally, we must have an antiferromagnetic coupling between the rare earth and the manganese, right? Although ostensibly this would depend on which rare earth I have in. And so this is not something we might expect to be transferable. So with this sort of minimal number of exchange values, we can explain most of the magnetic features we observe. And so the other two bits here are the anisotropies, the magnetic anisotropies. So again, manganese is always easy plane. So we can simply write it in this fashion here. However, the rare earth anisotropies are very complicated. And so we write that term in terms of these BLMs or ALMs. These are the crystal field parameters, and these operators, OLM, Stevens operators, which depend on the total angular momentum of the rare earth. So we've done a lot of experiments and written a lot of papers where we've gotten some insight into various parameters within this. I think there's 10 or 11 parameters here that need to be understood. And so now we'll start to talk a little bit about some of our results. And so the objectives we have in this study is, again, we want to understand and quantify these magnetic interactions and determine how they can lead to a variety of different magnetic phases, including some chiral spiral phases, scalar chiral phases. We also want to understand how spin dynamics can control these magnetic phases. I think I tried to explain that fluctuations of the rare earth moment can sort of change the effective parameters within this within this total model. And so we need to understand the spin fluctuations. Yeah. And finally, as a consequence of studying the magnetic excitations using neutrons, we, surprisingly found emergent magnetic excitations, which we couldn't explain from a simple spin wave model. And then lastly, if I can get to it, I can start describing a little bit about the magnonics of these ferromagnetic phases. And so what do I mean by, well, let's see, I have magnonics next. So here I've put together a roadmap of what to expect in the magnetic excitations in these materials. It's a very complicated system. So what I'm going to describe to you soon is some inelastic neutron scattering measurements, but these are what we expect to see. So these different panels down here are plots of the dispersion. So the bottom axis is Q at some point in the Brouillon zone. The vertical axis is energy. And I'm just going to step through turning on different interactions in this compound and describe what happens. So if on the left panel here, if I have a single monolayer, single Kagome layer, right, I get a dispersion that looks like these orange symbols here. Now, this dispersion looks exactly like the electronic dispersion I showed in the very beginning, and it should, because the dispersion only depends on the geometry of the Kagome layer. And so just like we have flat electronic bands and Dirac points and Van Hove singularities, we would have the same features in the magnons. Okay, so these would call Dirac magnons and flat band magnons. Now, I mentioned that we have bilayers of manganese, and these bilayers are strongly coupled. So if I turn on the bilayer coupling, I'll basically get two copies of this Kagome dispersion that sort themselves into branches where the precessions of the manganese within the bilayers are in phase, called even, and precessions where they're out of phase, called odd. And those are split by the bilayer coupling, right? So if I can measure the energy difference between odd and even, I can measure this bilayer coupling. So now, so that's sort of what I expect for the Kagome bilayers, but now I turn on the rare earth. So if the rare earth has no anisotropy, like gadolinium, then I would expect sort of a branch at low energies whose bandwidth was determined by this JMR, the exchange between the manganese and the rare earth. However, if the rare earth has anisotropy, so in this case, KT represents the rare earth or the terbium anisotropy, then that mode will be gapped out. Call this an anisotropy gap, if you will. And so by measuring this terbium dispersion, I get some insight into the rare earth anisotropy and the strength of the coupling to the manganese. And then this last panel here shows the dispersion of the magnons along the Z direction. So these dispersions will measure the interlayer competition between these exchange interactions. And so we can see that this lower band here, the even band, its bandwidth would be determined by the ratio of J1 and J3. However, the interesting thing is that the odd band, you can see that if J1 is ferro and J3 is antiferro, this dispersion has a band minimum at the zone boundary, at the A value, at the A point in the zone. However, if I reverse that and J1 is antiferro, J3 is ferro, it inverts, right? And so then the band minimum is at gamma. So we can look at these features in an inelastic neutron scattering experiment, and we can determine quite a bit about this magnetic Hamiltonian. And so one more bit about magnonics. Magnonics is sort of a field where people are interested in how information can be carried by either a magnon spin or a magnon chirality. And so when I have a ferromagnet, right, magnons are only right-handed. However, if I have an antiferromagnet, I have two degenerate modes, which have both left and right-handed copies, which in the absence of a magnetic field would have the same energy. However, a ferrimagnet offers interesting insight into magnonics because I have sort of an optical branch or an acoustic branch, which has a right-handed chirality, and an optical branch, which has a left-handed chirality. And these would be split by either the anisotropy or the exchange field. And so having these two and looking at the interplay between these two can address some open challenges in magnonics, like getting faster rates for transmitting information. How would you modulate the chirality? So for example, for information technology, or even how can I make a superposition of magnon chiralities to generate something which is equivalent to a magnon pseudospin? So how do I put the magnon on a Bloch sphere? And so these R661 compounds are actually an interesting system to study magnonics. So now I'll just go a little bit into what our approach is, and that's neutron scattering. So so neutron diffraction, we can determine the magnetic structure and the magnetic symmetry. We can relate this to the topological state. For inelastic scattering, of course, we can measure the magnetic interactions simply by measuring the energy cost for creating different plane wave excitations in the material. And that allows us to refine these magnetic models. And if we have good models, we can study magnetic phase stability and switching. And if we look at these nice magnons here, we don't see any evidence for coupling to carriers or coupling to any type of orbital motion. On the other hand, if we see damping or any novel effects in the spin waves, we could possibly relate that back to coupling to the Kagome carriers. Also, inelastic scattering is useful for measuring properties of quasiparticles in materials. Now, quasiparticles are just elementary excitations. It's exactly what we're measuring here. So magnons are a quasiparticle, but also spinons, Dirac magnons, flat band. These are all different quasiparticles which we can try to measure with neutron scattering. And so I won't spend too much time on this, but if people have questions about it, please ask. But neutron scattering is sort of the premier method to measure spin correlations. In time of flight neutron scattering, we essentially measure the imaginary part of the magnetic susceptibility as a function of wave vector and as a function of energy. So we have these large area detectors. These are huge instruments, right? The detector bank, you can see people inside the detector bank on Sequoia. It requires huge facilities and it requires huge samples to study. So this is big science, right? There's a lot of money, a lot of effort to doing these experiments. But what we get out of it is this four-dimensional space of excitations. It's a very information-rich set of data, and we can get a lot of insight into magnetic materials by being able to measure these energy scales. So now I'll start describing some of the work that we've done. So the first is, how do we develop this magnetic model for rare earth McQueeney-6 So I gave you this roadmap for the excitation. So here I'll just step through a couple of cuts that demonstrate these features. So for example, if I measure the dispersion here on the in-plane direction in an even Brillouin zone, I can see the even mode, which is like an acoustic magnon, and I see the rare earth mode. In this case, this is terbium manganese-6 So I see the rare earth mode here. If I move to an L equals odd mode, then I would be sensitive to the odd excitations. So I see the odd branch here. I see the splitting between even and odd. That will tell me something about this J2, which is very strong. You see the splitting is about 40 millivolts or so. Also, we can look at the OOL dispersion. Again, I described to you that you can see these. We have better data for this. This is just high energy, high incident energy, but you see the even modes here, which have a very narrow bandwidth. That's telling us that we have frustrated interactions. We also see the odd mode and sort of the fact that it's got a band maximum at gamma. That tells us that J1 is ferro and J3 is antiferro. So just from these two panels, we know a lot about the different exchange interactions, and even the energy of this terbium mode, which is about 20 millivolts, tells us a little bit about the anisotropy of the terbium.
So are these modes resolution limited, Rob?
Most of them are. I think the odd mode is not. As you go up in energy, they start to get broader.
I see. I mean, you don't see the optical mode though, right? You don't see the flat band though, right?
I'll get to that. No, we do see it, but it's not, it doesn't look like it would in a linear spin wave calculation.
Okay, thank you.
So we've looked at different rare earths. So terbium, holmium, erbium. Again, this is uniaxial, tilted, planar ferrimagnet. And we see that this odd mode behaves the same in all three cases. So we feel like these interlayer couplings are transferable throughout the series. We also see that the rare earth mode, so here it's about 20, but in holmium and erbium, it's below 10. So clearly there's differences in the magnetic excitations when I change the nature of the rare earth anisotropy. So these are all things to understand. So I can talk a little bit about different temperature-driven transitions. So like I said before, if you warm up any of these ferrimagnetic compounds, they eventually become easy plane. So for terbium, there's a transition from uniaxial to easy plane, a spin reorientation transition just above room temperature. So here's some neutron diffraction where we look, for example, at the 001 neutron diffraction peak. If you have uniaxial magnetism, this magnetic reflection is 0. However, when I have a spin reorientation transition, when the moments are perpendicular to Q, I'll get a jump. And so we can clearly see the spin reorientation transition here from uniaxial to planar. We can also get a look at the spin reorientation transition by looking at the magnetic excitations. So here's a set of dispersion panels. This is for modes which are within the Kagome layer, where we see the terbium mode appear at low temperatures, and we see these gapped even branch down here. And as we warm up, we see a couple things happen. One is that the upper mode vanishes, and the spin gap closes, And also at these intermediate temperatures, we start to see the development of another branch, which when I'm above the spin reorientation transition in the planar phase becomes a full-fledged mode. And so we identify this mode here as the upper terbium mode. This lower terbium mode is a property of this planar phase. So we spent a lot of time thinking about two things, right? Why does the upper mode disappear? And why at intermediate temperatures do I have both the upper and the lower mode at the same time? So from a simple point of view, it's easy to understand what drives this spin reorientation transition. So again, I have a terbium which is sitting in this crystal field environment and sitting in this environment of manganese spins. So if I just take the crystal field acting on the terbium, I'll get a bunch of crystal field levels, which in this plot B are shown with the molecular field of 0. But the molecular field of the manganese acting on the terbium is very, very strong. And so you can see here as the molecular field increases, all these terbium crystal field states, they split. And so this line here is about the estimated value for the molecular field acting on the terbium at low temperatures. And so this transition, so here we see that the ground state is sort of the -6 state of the terbium. That's just this uniaxial orbital state. And that there's a huge energy cost to excite the next crystal field state, which is this -5 state. But this is just the energy of the upper mode. So this energy is about 20 millivolts. It just gives me this. This is essentially a crystal field excitation, which is broadened by exchange. So as I increase the temperature, though, I start to occupy these other crystal field levels. And so what happens then to the shape of the orbital is it becomes more and more isotropic. So you can see here that, for example, if all these different crystal field levels are all equally occupied, I would just have an isotropic terbium. And so as temperature increases, the shape of the orbital goes from this pancake to this sphere. So I can use that information to calculate the classical anisotropy constants of terbium. And you can see that they're strongly temperature dependent. And as a matter of fact, if I take K1 plus K2 plus the easy plane anisotropy of the manganese, I can see that the anisotropy goes to 0 at the spin reorientation transition. This is based on the parameters we determined from the neutrons. So that's very satisfying. And furthermore, we can see that if you look in this upper panel here, that at 310 Kelvin, you can see that the let me say that from 2 Kelvin to 310 Kelvin, the anisotropy strongly softens due to terbium thermal fluctuations. And if I add in the manganese anisotropy, I can see that at 310 Kelvin, I have a situation where I have two minima that have the same free energy. And so this will then trigger a first order transition, which is what's observed here. So it's all very satisfying. And we can go back to the neutron data and we can use knowledge of these crystal field states to again, calculate the neutron spectrum through the random phase approximation. So here we would carry all the information of these crystal field states here and calculate the local Green's function and then calculate the coupled Green's functions. And this would be proportional to the susceptibility. So, and then we can compare the data to the RPA calculations, and we understand that the upper mode vanishing is a consequence here of the depopulation of the ground state. So as the ground state disappears, the Green's function, F is the orbital population, it drops and the mode disappears. And we see that the appearance of this sort of lower mode here, which we associate with an isotropic terbium, comes about because within this, this planar phase, we essentially have all of the different terbium crystal field levels almost equally occupied, right? So the interesting thing is, why doesn't it happen gradually? Why doesn't this mode shift down to lower energies as the temperature goes up? And so there's some mysteries here. The agreement with RPA and the data isn't perfect. And so we have a description of that in terms of an orbital alloy, which I don't have time to describe here. But when we take all this information, so we have the crystal field potential, so we know the crystal field levels, we know all the exchange interactions, we can introduce a magnetic field, we know the sizes of the moments, then we can use mean field to calculate the magnetic temperature phase diagrams for all the different compounds. And so this is a paper that we put on the archive just a couple months ago. This was done by an undergraduate here at Iowa State. So she had some code and she calculated all these phase diagrams. It's pretty cool. So we can see that you get a variety of different, so these are different phases labeled here. So VP is a vertical plane canted phase. We have general canting planes, ferrimagnetic phases, forced ferromagnetic phases, and so on. The point is that when you have a material that has strong magnetic anisotropy, exchange between these magnetic sublattices, and Zeeman energy, you can get a variety of different canted phases, collinear phases, non-collinear phases, and so forth. And as I increase the temperature, I'm just turning off the anisotropy because of thermal fluctuations. So it will squeeze out all these non-collinear phases in terms of collinear phases, or in the case of erbium, where the coupling between erbium and manganese is weak, it will allow us to see spiral phases. So these are great mean field calculations, and we're working with the folks at the High Field Lab to try to verify some of these calculations. So for example, in erbium-166, with the field along the B direction here, you would expect to see nested canted phases where the canting plane rotates by 90 degrees. That's what the mean field predicts. And in fact, we do see evidence for these sort of nested canted phases in the magnetization data. Another cool thing in the holmium is that we see when the field is along C, there'll be a transition between two vertical canted phases where the rare earth moment jumps from below the plane to above the plane. And so because these two phases have the same symmetry, right, they're both vertical plane canted phases, this can be first order or second order, right? And so at low temperatures, it's first order because the anisotropy is very strong. However, that barrier goes to zero. And in fact, in this phase transition here, this is just an analog of a liquid gas phase transition. This first order line terminates in a critical point. And then at temperatures above that critical point, it would become a sort of a continuous crossover between the two phases. It's like a fluid out here. And in fact, we're working with the Los Alamos folks also, and the prediction of this critical point here, don't pay attention to these colored ones. This blue one here is a strong first order transition, which terminates at a critical point at about 45 Tesla and 90 Kelvin. It's pretty close to what the mean field calculates. So we have a lot of these phase diagrams. It really tells you a lot about what's going on in all these compounds. So now, how much time do I have? What, Peng Cheng, when?
You have, let me see here, 10 more minutes.
10 more minutes?
Yeah.
Okay. So now I'm going to talk a little bit about some novel excitations, which we didn't expect to see from neutrons. So here I show, so based on all these parameters that we determined, we can calculate the expected neutron scattering spectrum from our model. And so again, we see here these low energy excitations, the even, the odd, the terbium modes, which we see very clearly in the neutrons. They're very sharply defined. You can see it over here in the data. And we would also expect to see very sharply defined flat bands, flat magnon bands, and these optical odd and even bands, right? In total, we should have 7 bands within linear spin wave theory. But we don't really only see the bottom 3. And instead of that, we see very sort of overdamped or heavily damped excitations instead, right? And so we split these up into 2. And so you can see here in this white rectangle is almost a vertical excitation, almost looks like an itinerant excitation, which is at what we call the gamma prime point in the Brillouin zone. So this is it's a zone center, but it's typically associated with chiral ground states, right? And in the yellow box here, which is centered at the K point, we see a different set of excitations. And so this white rectangle we see in multiple zones, right? So we see this broad excitation here. You can see this red curve here, which shows it as sort of a very broad excitation centered around 130 millivolts. This yellow one is higher in energy. It's about 175 millivolts, and that's at a different point, at a K point in reciprocal space. So one way we can get more information about these excitations is to look at constant energy slices. So if you look here, we would slice at different energies and look at the distribution of intensity in the reciprocal space. So as we move up from low energies to high energies, at low energies, we see, so let me just be clear here. So the solid curve, the solid points are gamma zones. So that's where you'd see acoustic modes. And the white circles are in the center of what we call gamma prime zones, where you would see the optical branches or other sort of modes that have a phase relationship amongst the manganese, which are within the Kagome layer. So at low energies, we see these acoustic modes very clearly. And as we move up and up and up, we eventually go above the top of the band. For these acoustic modes, you can see at around 100 millivolts, they're right at the edge of the zone. And then when we go above that, we see a pattern here in Q space, which consists of these bars, which go through the gamma prime zones. And now if you go backwards, you can see actually those bars exist at all the energies, going down to the lowest energies. And so if I go back here, I can see that's because I have sort of a vertical excitation, which is going here from about 50 millivolts all the way up to about 175 millivolts. So it has a characteristic structure in Q space. If I continue to go up in energy, right, I can get up above even this gamma prime excitation here to this yellow boxes here, these K excitations. And I can see at 200 millivolts, I can see the excitations are clearly centered at K. So we decided to think about this not in terms of the magnetic Hamiltonian, which would predict sort of these nice spin waves, but to think about these as localized excitations in real space. And so we can model those in two ways. So take the first one here. So this is where we have intensity, which is peaked at the K points. This is the highest energy excitation. And our first thought was, well, if it's a flat band, it should have a particular phase relationship amongst the spin correlations around a hexagon. Because we know that the flat band Wannier state, the sign just alternates around the hexagon, right? And it remains localized. So if we include that phase relationship here, we get this reciprocal space pattern, which exactly matches this sort of 200 millivolt pattern here. So we identify this 200 millivolt excitation with the flat band, although it's heavily damped. So what about this other one here, this lower energy one with these bars? So the logic here was that we know that if you have an antiferromagnet on a Kagome lattice, you can get what they call a chiral Q equals 0 antiferromagnet. That would have a Bragg peak in the gamma prime zone and would have a magnetic structure shown in these diagrams here. So there's some examples, right? Manganese 310 and so on. And these have a non-zero vector chirality. So we can take that pattern and we can assume that that describes the spin correlations of a single hexagon. We call this a chiral excitation. And lo and behold, the structure factor for that has these bars which go through the gamma prime zones, which again matches up with this data quite well. So we feel like these high energy excitations, they're not linear spin waves, but they fall into this flat band, which is actually expected from linear spin wave theory, although it's somewhat damped, and this chiral mode, which comes out of nowhere. So it's an emergent feature that could be associated with sort of the itinerant character of the Kagome layers. And so, again, we have measurements in different compounds, terbium, holmium, erbium, yttrium. All these have different magnetic ground states. They all have this same chiral excitation. So here in the terbium I just showed you, it's pretty prominent in this plot here, just going straight up. In holmium you see it, in erbium you see it, in yttrium you see it. If you look at the energy sort of the Q dependence at about 140 millivolts, you see it has the same characteristic feature of a chiral excitation. So the take-home message here is it doesn't matter what direction the magnetization is pointing, you always have a chiral mode. So it seems to be just a property of a single Kagome ferromagnetic layer. So I have 4 minutes. So I can show you some new results now.
Okay. Please, yeah.
What's that?
Please, yeah.
Okay. So we talked a little bit about spin chirality, and so we have some new results, neutron results on the development of spin chirality, these compounds. So let me just refresh your memory. So in RMn6Sn6, we have a temperature-driven transition from a ferrimagnet to a triple spiral phase. Here we can see down here a plot of the triple spiral wave vector, which is the spots here, in comparison to our mean field calculations, which is the line. So we get very good agreement of the temperature dependence of this spiral. And so it's an interesting system to study how a chiral or a vector chirality state spontaneously develops out of a collinear magnetic state. So if we study the magnetic excitations as a function of temperature, it tells us a little bit about how that happens. And the other point I brought up was about whether or not there's a scalar spin chirality as an applied field. And again, because applied fields can give you these distorted conical phases, we can discuss whether or not those phases have a scalar spin chirality or some emergent chiral field. So for the development of vector chirality in RMn6Sn6, we have this preliminary data here in the top right, which shows the dispersion along OOL of the RMn6Sn6. And so we see 2 branches. The upper branch is the erbium mode. So this is like a crystal field. And the lower branch is the even mode. But we see that it's split. It has a split minimum. And so that split minimum is, again, due to competing interlayer exchange. So if we introduce that in the model here, we can see that it's sort of like a soft mode almost, right? The system is ferrimagnetic, but it knows it has a tendency to move towards a triple spiral, right? If we can lower this JME exchange energy. And so we can do that by increasing the temperature. So here, this is all data, where as we increase the temperature, we see for the sharp dispersion along H, a rapid closure of the spin gap. And along L, we can see again this double minimum, which again rapidly closes. And then at 100 Kelvin, we're in this spiral magnetic phase. So it's this sort of split minimum here is replaced by real incommensurate excitations, a real incommensurate ground state. So it's kind of a satisfying picture of how that evolves. And we're working on RPA models to give us a better understanding of really the full picture of what's going on. So a more interesting case is when you apply a magnetic field. So this TCS phase, in principle, it has a scalar spin chirality, but it doesn't have an emergent chiral field. And the emergent chiral field is what you need to give you a topological Hall effect. It's the field that the electrons would respond to. So I can write the emergent chiral field B alpha as this triple product of M times the derivative of M in 2 different real space directions. But the TCS phase, which is this upper right, just shows the static magnetic structure as a function of Y and Z. Again, the planes are always ferromagnetic. The magnetization only varies as a function of Z. So this is strictly 0, right? However, there's a theory that if you introduce magnetic fluctuations or magnons, that you can add to the static magnetization an additional field, a magnon field mu, and that field can vary in the orthogonal direction, say Y, the Y direction. And so this is a theory, what they call fluctuation-driven scalar spin chirality, which was proposed by Geimeier and Mazin et al. And so we've looked quite in detail at this. And so if you have a transverse magnon in the TCS phase, this lower picture, the arrows show the total magnetization field. It includes the static magnetization and the magnon field. So the colors of the arrows then are whether the magnetization is pointing along X or Y. but we can evaluate the emergent field, which is the color scale here, right? And it's 0. So if I have a transverse magnon in a TCS phase, the emergent field is still 0. So we're struggling to understand why both our analytical and numerical calculations show us that no chiral field emerges from transverse magnon fluctuation. So I think it's still an open question what's going on here. And so again, we don't understand this, but we have measurements of the dependence of the magnons as a function of field out of the spiral phase. So this data is taken at 200 Kelvin, which is within the spiral, zero field spiral phase. And as I increase the field, I can see I have a incommensurate or a distorted spiral. I still have these nice incommensurate excitations. But when I enter the TCS phase, I have a lot of low energy spectral weight, sort of that covers some range of L. And then at higher fields, I return to the ferrimagnetic phase, which looks like the same as the zero field low temperature ferrimagnetic excitations. I have a small gap and I have these sort of split minima here. So we've developed a model by basically doing energy minimization of a large set of spins where we can find the model parameters that give us the incommensurate spiral, triple spiral, and also give us some evolution of these states as a function of field. So this on the left here, this is a calculation of the model magnetization going from distorted spiral to TCS to forced ferro, which you can compare to the measured magnetization, which I scaled here. So we're still working on it. We don't know quite what it means, but we're a little puzzled about this fluctuation theory. But we hope maybe there's something here in this neutron data that's revealing maybe an alternate mechanism than the one that's proposed, which we think might have some issue. So I think I'm out of time.
Yeah, you're out of time. Yeah.
Yeah, I mean, I could talk a little about chiral magnon mixing. If somebody asks, I can, but I'll just move to this.
Okay.
So in summary, right, we've determined the magnetic excitations in these material. We found that a lot of these interactions are transferable across the series. The crystal field potential is transferable. This allows us to know quite a bit about the different magnetic phases that can appear. And in terms of chirality, we've observed these chiral quasiparticles, which exist within the Kagome layer. We observe them in all compounds that we've measured. And so we're also looking at evidence for how magnetic excitations couple to the development of spin chirality, and including this mechanism for fluctuation-driven scalar chirality. And I'll skip the magnonics stuff, but that's what I wanted to talk about. So I'm happy.
Thank you very much, Rob.
Thank you.
Yeah, fantastic talk. Yeah, really enjoyed. Learn quite a bit. Yeah. Let me ask you some questions. I mean, I guess I'm sure the audience will have questions as well. But how do you actually understand that your low energy stuff, can be relatively well described by a simple Heisenberg model, yet your relatively high energy stuff, you need this sort of a cluster type of excitations to actually describe it. I mean, how do you view this from holistic perspective?
Well, the way I think about it is so you have these acoustic modes, which you can have these odd and even acoustic modes, and in that case, right, if you look at the manganese Kagome layer, right, there are 3 different manganese within a Kagome layer within the unit cell, right? And then there's another 3 in the next layer, right? But in those acoustic modes, the manganese are always processing in phase within one layer. When I move to the optical modes or the flat modes, the manganese within a single layer have some phase relationship between them. So the second they're not rotating coherently in phase with one another, they start to get damped. And that's the simple explanation.
I see. I mean, so have you actually checked to see what the total moment sum rule is about, that you can really get the total number of spins to be consistent with your expectation?
I haven't done that, no.
Okay. I mean, your idea of this, the latest idea is really quite interesting in terms of topological Hall effect. So you're basically suggesting that the interpretation by the Boston College group, may not be correct, right? At least, you cannot confirm it, right?
Yeah, we thought a lot about the analytical part of it, right? And so when you define this magnon field, right, in the paper by Geimeier et al., that magnon field, there's some freedom to choose that magnon field. For example, you can have the magnons precess in a plane that is not perpendicular to the magnetization direction, right? Now, typically in a magnon, you wouldn't allow that to happen. But if you do allow that to happen, then this magnon, the chirality is not zero anymore. But its sign would alternate from along Z. So if I average along from layer to layer, it would average to zero.
So you will still not get a topological Hall, right? Yeah.
Right. So it depends. A lot of it depends on how you think you should be doing the layer average. But there's other types of averaging which can make it zero. So for example, the TCS phase, when you look at the TCS phase, right, what you have is a cycloid which is propagating along Z. But that cycloid can propagate left or right. And there's nothing about the application of a field that would pick one over the other.
Yeah, so, because the material itself is central symmetric, right?
Right. So
emergent symmetric, right? Yeah.
So the sign of the emergent field depends on the handedness of the TCS. So if I have a domain where it's left-handed and a domain where it's right-handed, it would also average to zero. Unless there's some other interaction that is only allowing the conical cycloid to go in one direction, only one sense of rotation, right?
Yeah,
and then you also have to have non-reciprocal magnons. So if I'm choosing a magnon along Y, right, the one along minus Y can't give me the same contribution to the chiral field. Otherwise, it will average to zero.
No, I completely agree. I mean, unless you can, look at crystal structure to see whether there's actually inversion symmetry breaking, right? There's no evidence of that, right?
Not that I know of. Yeah.
Very, very interesting. Yeah, no, I mean, it's still a big puzzle.
And so, the one thing is that, maybe the magnons aren't nice coherent magnons, right? So here, the assumption is that the magnon field just forms a precessional magnon where I can write it as a plane wave, right? And then once I do that, I can evaluate this. I can evaluate this in a continuum model. I can just evaluate this emergent field, right? But maybe it's not. I mean, if I look at these types of excitations, right, what you see in the TCS phase, it's kind of interesting. Within some range of L, there's essentially no gap. And so you could think of that like as forming a wave packet of some kind along L.
So maybe you mean longitudinal mode of some sort.
Yeah, I tried that. So if you assume mu is longitudinal, you also get zero.
I see.
So, but it could be that it's there's a description of it which is more like a localized mode, which I think the data is kind of pointing towards. But you still have to encounter these other averages, averaging over the magnon direction or the handedness of the cycloid. Somehow you have to overcome these.
No, I completely agree with you. I mean, I think Igor Martin's picture on this is basically quite intuitive, right? I mean, it's really not direct proof. Yeah.
Yeah, and I think under the assumptions that he makes, you can show that it's not zero with those assumptions. But I think the question is, what is the right assumptions? Maybe I mean, maybe my assumptions are wrong. And calling it exactly zero is wrong, but I did the math and then I did it numerically just to check myself.
Very, very nice. Yeah.
And you get similar results, but I don't know. Is Igor on the? Is he here?
I don't think he's here. I haven't seen him yet. He might get upset. Yeah.
Yeah.
Okay. So any other questions for Rob? It was a fantastic talk. I mean, I really enjoyed it. Yeah. Any other question from the audience or students in particular? I mean, you should ask, right? Rob is a neutron expert. Anything you can ask him anything. Wow. Yeah, like my typical class, it's very, very silent. You're not clear with it. I understood what you're talking about.
It was too clear.
It was too clear. Okay, yeah, thank you very much, Rob. Yeah. It looks very nice. Yeah.
All right.
Yeah, thank you for giving this talk. Yeah.
Sure thing. And so you're going to post it. I
Yeah,
mean,
we're going to post it tomorrow. Yeah.
If anybody has questions that come up afterwards, if they think about it or they watch the talk, just, send me an email.
Yeah.
And, again, Peng Cheng or Jeff, some of the folks here who might have some insight into some of this neutron data and whether they have some ways, especially to think about this